Hello everyone, this is part 11 of the probability distribution video series. So in this video, we are going to talk about the infamous Dirichlet distribution. Now, if you want to learn about this distribution, the first thing you need to do is to understand the beta distribution, which I have described in the previous video. So if you don't understand beta distribution, it will be very hard for you to understand Dirichlet distribution because Dirichlet distribution is nothing but the multi-class version of beta distribution. So let's dive in. So first of all, Dirichlet distribution is probability of more than two outcomes. Let me say this again. Probability of more than two outcomes. So let me explain this with an example. Suppose after the first week of starting a cancer treatment clinic, the clinic has 5 lung, 3 breast, and 2 colon cancer patients. So the question is, what is the probability of a patient coming with one of these 3 cancer types after the first week? The question is very simple. I'm pretty sure that this is your answer. So you simply divide by the number of patients, by the number of patients of a particular cancer type, for example, lung cancer, by the total number of patients, right? So you do this for every cancer type, and then you get these answers. So let's move forward. Fast forward the first 4 weeks. So after the first 4 weeks of starting the clinic suppose now has 50 lung, 40 breast, and 10 colon cancer patients. So in this case, I'm asking you the same question basically once again. So what is the probability of these cancer types? So this will be your answer, right? So you see that your answer has changed. 0.5 remains the same, 0.3 has become 0.4, 0.2 has become 0.1. Now understand that it's the same clinic, but your answer changed as you were exposed to more samples or more patients. And your answer will keep on changing as more weeks pass. So, given that the clinic has total 10 patients, let me ask you a few questions. What is the probability of P lung equal to 0.5, P breast equal to 0.3, and P colon equal to 0.2? What is the probability of that? So understand that this is why it is called the probability of probabilities of more than two outcomes. So there are 3 outcomes here. So why are we trying to calculate the probability of these probability values? This is because these probability values are actually changing. And obviously, initially, after the first week, we were not that confident about our predictions. But I think after the first 4 weeks, we were a little bit more confident about the probability values. And I'm pretty sure that after 1 year, we are going to be much more confident about what is the expectation of the number of patients or the probability of the different cancer patients that will come in our clinic. So again, the same question can be asked for P lung of 0.4, P breast of 0.4, and P colon of 0.2. Same question for some other values. So the moral of the story is we can have infinite possible such cases where P lung plus P breast plus P colon equal to 1. I mean, these are probability values, so they have to sum to 1. That means this is a probability distribution where there are 3 random variables. So this is random variable number 1, this is random variable number 2, and this is random variable number 3. And they add up to 1. And since we have infinite possible such cases, this is nothing but a continuous probability distribution. So this is just like beta distribution. So those of you who know beta distribution already know what I'm talking about here. And again, you need to actually see the previous video to understand this at its full glory. So if we had 2 cancer types instead of the 3 cancer types discussed here, we could simply model the problem using beta distribution. Because then what we could say is, suppose we have lung cancer and colon cancer, we could say that if there is lung cancer patient, then we have a success. And if there is colon cancer patient, then we have a failure. But for more than 2 cancer types, 3, 4, 5, 20, anything, we need the Dirichlet distribution, which is the multi-class version of the beta distribution. For the 3 cancer types, we are going to have 3 random variables, where these random variable probabilities or these random variables will add up to 1. And those random variables will be greater than or equal to 0 because they represent probability, right? Okay, nice. So I mean, I've written here greater than or equal to 0, but in reality, they should be between 0 and 1, basically, because these are probability values, so they have to be between 0 and 1. Okay, so for this case that we are discussing, 5 lung, 3 breast, and 2 colon, these will be the different alpha values. So the alpha values determine how the digital distribution will behave or how the distribution PDF will look like. So alpha 1, alpha 2, and alpha 3 will be 1 plus the number of outcomes of that particular class. For example, we have 5 lung cancer samples, so alpha 1 equal to 5 plus 1. We have 3 breast cancer samples, so alpha 2 equal to 3 plus 1, and so on and so forth. So let's try to visualize this distribution a little bit. So suppose this is a triangle and the 3 heads of the triangle represents 3 extreme cases. So in the first case, the probability of lung cancer patient coming up is 100% and the other 2 cases are 0. Here, the breast cancer is 100%, the other 2 cases are 0. And finally, here, the colon cancer case is 100% probable, the other ones are 0. Now, according to what we observed so far, we know that lung cancer is the most likely. So we see that all these points, these are randomly sampled points from this triangle, the distribution. So everything inside this triangle is, you can think of it as the probability distribution of this Dirichlet distribution. So what we can do is we can randomly sample from this distribution and we are going to get points which are scattered like this when we are going to randomly sample the points. So let me explain why they look like this. So we have the most amount of lung cancer samples. So this cluster of points, they come from very close to this particular point. Then we have 3 breasts, so it's a little bit farther away from the breast cancer point. And finally, we have only 2 colon, so it is the farthest away from the colon cancer point. Now also understand that the randomly sampled points are actually scattered out quite a bit. This is because we only have 10 samples here. But what if we actually 10x our samples? So if we 10x our samples, you can see that instead of 5, we have 50 lung cancer. Instead of 3, we have 30 lung cancer. Instead of 2, we have 20 lung cancer. And alpha 1, alpha 2, and alpha 3 is 1 plus those numbers. In this case, the points cluster in the same place, but they are now clustered together and clumped together very tightly. That means when we randomly sample from this distribution, the distribution is much more cluttered, much more skewed in this small place. This is because now we are much more confident about what the probability values should be. So that is basically the impact of number of samples in the Dirichlet distribution. Then let's talk about the probability density function of the distribution. So general formula for the beta distribution was something like this. So you saw this in the previous video. We had only one random variable b, was the gamma function, which is equivalent to n minus 1 factorial, where n can be any positive real number. So they can be floating point number as well. So formula for Dirichlet distribution with 3 possible outcomes will be, it will have these 3 random variables, these 3 parameters. You can see that we are adding up the alpha beta, we are adding up the 3 alphas, we are multiplying the gamma functions, we are also multiplying the gamma functions, we are multiplying all the possible p's. So in the beta distribution, we have the p, the probability of success, and 1 minus p is the probability of failure. Here the 3 probabilities are p1, p2, and p3, so they have been multiplied with the exponent on top of them. So it is actually the same as beta distribution. So you can generalize this formula for the k possible outcomes. So it will look like this. So I've just written the summation of all the k parameters and to the gamma function of it. I've also multiplied all the gamma functions of all the k alphas, and also I've multiplied the k p's or the k random variables with their exponents. So let's now look at the expected value of this distribution. So in the beta distribution, it looks something like this. So obviously this particular distribution has many random variables. So for our example case, we have 3 random variables. So we need to get 3 expected values. So for k random variables, we are going to have to take k expected values. Okay, this is the difference. This is the first difference, because in beta distribution, we had only one random variable, and so we had only one expected value. But this time we have 3 random variables, so we should have 3 expected values in this example. So how do we get to that value? So we can simply integrate from 0 to 1, because that is the range of the random variable, because it represents probability, right? And I've written bold p and bold alpha here because there can be many p's and many alphas based on the number of outcomes, the number of possible outcomes. So if we do the integration, then we are going to get alpha 1 divided by summation of all the alpha i's. This is the EP1. Similarly, for EP2, the numerator will have alpha 2, and for EPK, the numerator will have alpha k. So understand that in the EP1 case, this was the formula you can see here. We can write alpha 1 as n1 plus 1. So n1 is the number of samples in outcome 1 or class 1. And alpha I means there are there are n1, n2, n3, all of those things. So if we add all of those things up, we get the total number of samples n. And for each of the k cases, we have plus 1. So we have plus k here. So when we have large enough sample size, this will turn out to be n1 by n because 1 and k are constants. So what is n1 by n? This is nothing but a normal probability. So this is how we normally calculate probability. So we simply take the number of samples from one class and divide it by the total number of samples. So when we basically have a lot of samples, then Dirichlet distribution probability, or expected value I should say, is actually the same as how we get the probability normally in layman's way. Let's also look at the variance formula here. So in beta distribution, this was the variance formula. So obviously in Dirichlet, there will be 3 variances for 3 random variables, and if there are k random variables, there will be k variances. And this is how the variance formula looks like. It is again very similar to the beta distribution because here you can say summation whole square, summation plus 1, summation plus 1. Then there is alpha, and beta means that everything else except for alpha. So here everything else except for alpha 1. That is why minus alpha 1. So Var-P2 is similar, alpha 2 and alpha 2 will be here and everything else is same. And so you can guess the other ones as well. So what does this formula mean? Let's break it down. So if we break this formula down, we can break it like this into 3 different fractions. We can then replace these things by the sample numbers. For example, alpha 1 can be replaced by n1 plus 1. Alpha I can be replaced by n plus k. So this one is actually more critical because we can actually just cancel these summations out. So it will be 1, and then the next part will be same as the first term. So we have this term right here, same as this. And we have n plus k plus 1 right here. So now the same thing, when the sample size will be large, these constants will not make any sense. So those constants will just go away. And so we know that n1 by n is nothing but p1. This is how we get probability of class 1 in normal sense. And 1 minus p1 is nothing but the probability of failure or something like that you can think of. And this is 1 by n. And this formula is actually very familiar to us. If we do the square root of this formula, we are going to get the standard error. So it's a very nice property that this Dirichlet distribution can actually give us the standard error and the expected value correctly when the sample size is large for multiple classes. So that is all about Dirichlet distribution. If you like the video, feel free to subscribe and share. And also there is a link in the description for donation. You can donate to our channel if you like to support our contribution. Thank you very much.